This is a toroidal propeller. It gets its name from the blades, which are in the shape of a torus, which is often described as resembling a donut. However, these special donut-inspired blades are much more impressive than they first appear. In fact, they have proven their ability to more than double the propeller efficiency when used on a boat, which greatly increases speed and fuel economy. Not only that, but these propellers can massively reduce the noise of both drones and boats. In this video, we'll see how it does this and some examples of it in use. The physical difference between the toroidal prop and a standard prop is obvious when you look at them, but it is not immediately obvious why this has such huge benefits. However, if we look at these two operating next to each other, things start to become a bit clearer. Firstly, this is a comparison between a toroidal prop and a standard prop. You can see far less bubbles, known as cavitation, coming off of the blade tips, even though the blades are the same size and rotating at the same speed. This is because the toroidal prop generates less tip vortices, which can cause noise, vibration, and reduce efficiency. It is believed to do this because the vortices that would develop at the tips are instead spread across the whole blade. In this second comparison, we can see that the toroidal prop also brings in more surrounding fluid as it spins than the standard prop, as the die from further away is pulled into the blade. This gives a further increase in both efficiency and thrust. The two main toroidal propellers I've seen is the one from Sharrow, who have been focused on marine applications, and one from a research group at the Lincoln Laboratories within MIT, who have been focused on extremely quiet drones.
We came up with this initial concept of using this toroidal shape, this annular wing shape, to make hopefully a quieter propeller. So I had an intern of mine run with the idea, where he took the concept and created a bunch of iterations to try out basically different shapes and see, what works, what doesn't.
The main difference between the two propellers from MIT and Sharrow is that the Sharrow blades have a more aggressive pitch, and the holes in the blades are smaller and less noticeable. This makes them more suited to their respective uses in either air or water. To demonstrate the noise reduction between these propellers, let's listen to a boat using a standard and toroidal one. This is a pretty insane difference and can be seen on drones too, where these graphs show that a standard prop generates much more noise in the important frequency zones than a toroidal prop. On top of that, if we consider a boat with a motor running at 4,000 RPM, the toroidal propeller efficiency is 205% that of a standard one. The toroidal prop also approaches maximum efficiency much sooner than the standard one, which is highly beneficial as boats spend a lot of time cruising at the mid-range. These combined mean the toroidal prop gives incredible average fuel savings of around 20%. The benefits of faster, quieter, and more efficient ships can't be overstated, as it could decrease sailing time, reduce fuel consumption and emissions, and reduce noise pollution to marine life, which is an increasing threat in our oceans as it affects their communication and navigation. These benefits are especially important if the props could be used on large cargo ships, which are the backbone of global trade, travelling thousands of miles across the world's oceans to transport everything from electronics to food to raw materials. In terms of the boat's operation, it is said to increase handling from those that have tried it, and it increases thrust in the reverse direction. For drones, on the other hand, more efficient flight may enable new possibilities for air travel and reduce disturbances to people and animals nearby. Clearly, this propeller has many benefits, but what are the drawbacks? The main one is that the complexity of the prop makes it more expensive to manufacture, as they are currently made using CNC machines or by being 3D printed. This makes the Sharrow prop cost around $5,000 compared to $500 for a standard one. However, as the boat would be cheaper to run due to its increased efficiency, it could earn this back over time. And if these become more popular, the cost will come down due to the economies of scale from mass manufacturing. It is also not fully clear how these will scale up to the larger ships or aircrafts just yet, as these generally use slower motor speeds. However, it is likely some benefits could come from this. This is also just the tip of the iceberg, There could be many more applications to come that we don't even know about yet, from highly efficient hydro generators to quiet computer fans. As you're still watching, please subscribe to the channel, as I think you'll enjoy some of the other videos that I make, like this one on a hydroelectric generator that can deliver cheap, constant electricity thanks to their new breakthrough.